Okay, let's turn next to the confidence intervals for the population proportion. And let's first review again what the intuition of that is. And let's derive those formula for the proportion using again an example. So we have a population where all the observations are either success or failure. So let's assume I have an observation of 10,000. So let's create a column of 10,000 observations. And we fill that a series, a step value, and we end at 10,000. 1, 2, 3. Okay, so now what does a proportion in a population look like? So we have our values, the xi's, but they come now from a Bernoulli distribution. It's basically success or failure. So let's assume we create a series, we go to data analysis, and then we can select the random number generation, and we select we generate 10,000 observations, number of variables 1, number of random numbers 10,000, and we want that to come from a Bernoulli distribution. And so the probability of success is, let's say, 0.2. And if you want to get the same sample as I do, we can use again a random seed, and of course we will use 42. And where do we want to display the 10,000 observations? Not in a new worksheet slide, but right next to my list of 1 to 10,000. So the output range starts, okay, it ends in cell B 10,001 and starts in cell B2. Okay. So now Excel generated 10,000 observations where 1 is a success and 0 is a failure. So think of it, those are 10,000 citizens, and we asked them whether they go regularly swimming. And 20% said, yeah, we go regularly swimming. Okay, so now in those 10,000 observations, we have a mean. And the mean is simply equal to the average of all those observations. And here it is 0.197. So it's roughly 0.2. If we remove a decimal point, it is 0.2. So if you still remember when we talked about the binomial distribution, then we said what is the standard deviation or the variance. So the variance is equal to the success probability times the failure probability. So that should be equal to 0.2 times 0.8. Okay, that would be 0.16. And then we have the standard error, and the standard error is actually defined. So we have the sample, that we have the variation, the variance of a proportion, that is the success probability times the failure probability, 1 minus p, and the standard error is actually the square root of the success probability times the failure probability divided by n. Okay, so let's actually verify that. So So what we do is we have here our population, and let's quickly take 1,000 samples. So this will be sample 1, and now I create a series to the right that I fill by 1, and I stop at 1,000. Okay, and so now let's say I take from that sample of 10,000 observations always a sample of 100 people. And I asked them, do you go swimming, yes or no? So the way to do that is again to use the VLOOKUP. So we say VLOOKUP, and then what do we want to look up? A random number, rand between open parentheses 1 and 10,000, comma, then Excel wants to know where is the table array. So in my case that is from A2 to B 10,001. And then if Excel finds that random number in the first column, I want the second column, so comma 2. Otherwise it is false, meaning don't look for something similar. Okay, so now my first observation is a 0, and now I copy down that formula 100 times. Okay. And actually what I should have done before I copy it down, I should have fixed the range so I can actually copy it. So the A2 to B 10,001, I need to put the dollar signs around. Okay, so now let's do it again. Okay, so now I can copy this formula to the right 1,000 times. So let's highlight the range where I want to copy to the right. And now I copy to the right. So now what I do is for each sample, I calculate again the mean. And then I display the sampling distribution for n equals 100. So equals average. So for the first sample, I get an average of 0.17, and now I copy this formula to the right. And now I copy that and I paste it into a new sheet, and I paste it transpose. So I go to actually paste special, and then I say I only want the values and I want to transpose it. I said I only want the values because whenever you have a formula active and you click on something, Excel recalculates everything. Okay, so now I have here my 10,000 samples. So the 0.17 comes from the first sample. Okay, let's create a list of 1,000. And here we have the sample proportion actually. So you can see in the first sample we got the proportion of 17%, and in the next one again 17, but then 22. So what I want to show you is that the standard error of such a sampling distribution of a proportion should be equal to this. So that would be equal to 0.2 times 0.8 over the sample size 100 square root. And then what do we get if I just calculate it theoretically? So that should be equal to the square root of 0.2 times 0.8 divided by 100. And then I get 0.04. So now let's double check. First of all, I calculate the mean for the proportion, so that is equal to the average. So that is indeed close to 0.20. So the sample proportion is also an unbiased estimator. And now let's take a look at the standard deviation of the sampling distribution. And that should be 0.004, which I forgot to write here, 0.004. Okay, so now let's see what we get. Equals standard deviation sample of all those sampling proportions. And it is indeed 0.039, but you can see that it is basically 0.04 if you round it to 2 digits. So this is the standard error here. So this is an important formula that we need for the proportion. So this formula here. So let's just write it again nicely. So the formula for the proportion is, so we have the X% confidence interval. We have our sample proportion, like 26% or 23%, plus minus. And now comes another nice feature, which is the fact that when it comes to the sample, whenever it comes to the confidence interval of the sample proportion, we can just use the z-score. And so now we use the alpha half, and that alpha half is equal to 100 minus x over 2. So if you have the 90% confidence interval, I have to find the z-score, where I have to the left and to the right so for the 90% confidence interval, I want to have here 5% and there 5%. Okay, and then times the standard error, and we just derive the standard error, no, there's no arrow, as the observed proportion of successes times the observed proportion of failures over the sample size, which was in our case 100. So why do we only use the z-score when it comes to the proportion? The answer is that when we use a continuous variable, we have much more uncertainty, because first we need to estimate the sample mean, and then we have to also estimate the population standard deviation. So because the standard error only takes one variable, p, the estimated proportion. But for a continuous variable and the confidence interval for the population mean, we said, okay, that's x bar plus minus a t-score times the sample standard deviation. But part of that sample standard deviation we already have, that is an estimate for the population standard deviation, so that's the first estimate, but it is estimated also by an estimated mean. So that just generates more uncertainty, which we don't have here. We only have a sample proportion, and that sample proportion alone is the proxy for the population proportion. So we have less uncertainty associated with the proportion. But yeah, to make a long story short, we can always use the z-score. So because we don't have to estimate first the mean and then estimate the population standard deviation, here we can estimate the population standard error simply from one estimated value, which is the population parameter. Okay, so which formula is used to compute the confidence interval for the population? Proportion pi, and that is, okay, it needs to be a z-score times the square root of plus, well, yeah, it should be b. Yeah. So it is z alpha half plus minus, so the estimated proportion plus minus z alpha half times the square root of p times 1 minus p over n. Okay, so now the problem set consists of, again, many questions. What I want to avoid now is to calculate them over and over again. It will become repetitive. So what we do is, let's just create a similar experience like this one, but for the proportion. And in fact, I call this one confidence interval for the mean, CI mean. And I don't need this sheet anymore. I can delete that. I can delete that. I don't know what's, okay, and I delete this one as well. Okay, and now let's create a new sheet. And I call that the confidence interval CI proportion prop. So now we do again the same thing what we did earlier. So similar scenario, but it's actually a little bit easier because we don't have to distinguish between a t and a z. So let's define first again our input panel. And we have again a value. So what do we need to ask the individual user? So the first question is, what is your sample proportion? And if you want to be very accurate, you can put in parentheses, you know, between 0 and 1. Okay. So let's take a look at our, no, let's not look at, let's first, actually no, let's do question 12 quickly because that's important too, and maybe we can incorporate that into our model. So it says, before using the normal distribution to construct a confidence interval for a population, which rule of thumb conditions must be satisfied? And the answer is that your n times p should be greater than 10. So that is the rule of thumb. If that is the case, then your sampling distribution will look normal, approximately. So n times p must be greater than 10, but also n times 1 minus p needs to be greater or equal to 10. So that is the rule of thumb. If those two conditions are met, then the distribution of the sampling proportions typically look like the normal distribution with mean p, just call it now x bar, with the proportion, and the standard error being p times 1 minus p over n. So those two conditions are important, and we can incorporate that into our model here. So n times p must be greater than 10, and n times 1 minus p must also be greater than 10. So So what is your sample proportion? Actually, we can already test our model for question 13. So in a sample of 200 voters, so that is our sample size. So that's the next question. What is your sample size? Okay, so here this is 200. Okay, and then 120 say they support a particular ballot measure. Okay, so now the proportion that we enter is 120 divided by 200. So we have a proportion of 0.6. Then what we need next is, what is your level of confidence in percent? So which is 0 to 100. We can put that also here, just to make that clear. So here we want the 95% confidence interval. 95%. Okay, so this is again our input panel. So we can format it nicely, and we can make that again a cell style corresponding to an input. Maybe center it. And okay, so now we have the output panel. Okay, and then value. Okay, so what we actually can do is we can now add here the output panel. We can answer the question, is your sample large enough to approximate or to use the normal, distribution? Or is your sample large enough to assume normality? Then it's a little bit shorter. To assume normality. Okay. So now we enter here, yes, whenever the success probability times n is greater than 10 and the failure probability times n is also greater than 10. So we can put that into an if-then formula, equals if. So now we will say and, because we have two conditions, and. So if 0.6, so we click into the cell where we have the 0.6 times 200 is greater or equal to 10. And so now we have the second condition, and now we put in parentheses 1 minus the 0.6 times n, the 200, which is P3 in my case, is also greater or equal to 10. Then we close the parentheses, comma, then what's the value if true? Then you say yes. And otherwise, we can write in quotation mark no, no, and then maybe another alert that says no, use results with caution. Okay, something like this. So you see, if I had a very small sample size, maybe only 10, It says no, use results with caution, because now the condition is not met. But we had 200. Okay, so the next thing is we have to say your relevant z-score is, your relevant z-score is, okay, so that's easy because now we don't have to distinguish between the normal and the t-distribution. So we just use the z, and that is equal to norm dot s inverse, and the probability we determine again by by subtracting from 100 the user imputed level of confidence, which is now 95. Okay, let's put the 100 minus cell B4 into quotation marks, and then we divide by 100, and then we divide by 2. Okay, and that's it. So now we get negative 1.96, and here in the question, in case you don't have maybe Excel readily available, we use 1.96, but that's also confirmed here. Okay, so, and let's put all our, let's center everything again, and again let's remove the negative, so I absolute this formula again. Okay, so 1.96. So it's the same as here. And now we can write again that equals, now we say your, and then we close with quotation marks, and we put an end, and then we pick up the 95 from cell B4, and then we use again and now we continue the text. Your 95% in quotation mark confidence interval lower limit is colon quotation mark. Okay, so that's it, and this time I want to fix the B4 with F4. Okay, maybe there's a space missing, and 95, maybe let's actually do it like a percentage sign. Okay, your 95% confidence interval lower limit is, and now we can do that for the upper limit. I just copy down that formula with Control D, and then we change the lower to upper. Okay, and now we just calculate it. So that is now equal. We can also add the standard error. So let's insert another row quickly, and it says your standard error is. And by the way, the standard error is often reported when you see a poll. So let's say if you see a poll where somebody was surveyed, or a bunch of people were surveyed on a certain topic, you often can see at the bottom of the survey the standard error is 0.03% or so. So that's why I want to report it. And again, our standard error is the square root of the success probability, which is in this case 0.6, times the failure probability, which is 1 minus 0.6, but of course you cannot enter 0.6 and hard code that, so you need to keep that flexible by going to the respective cell, divided by the cell where we have the 200. And now we actually have a standard error of 3.5%. Okay, but now we are done, and we can calculate the lower limit, which is equal to the sample proportion of 0.6 minus the relevant z-score times the standard error. So let's remove some decimal points. We don't have to put it in yellow, but center. And now we do the upper limit, which is equal to the sample proportion plus the relevant z-score times the standard error. And again, we just copy the format from above, and now we have 0.532 to 0.668. And we have a very nice interactive dashboard where we just enter what we need, and then we can get the results right away. And again, we can make that an output panel. So if we want to format the cell style to an output, then we can format it like this. Okay, so now it says a market researcher finds that 35 out of 100 surveyed customers prefer brand A. Calculate the 90% confidence interval for the proportion of all customers who prefer brand A. Okay, so that's pretty straightforward now. So now we have a sample size of 100 and 35 like the brand, so that's 0.35. And now we want the 90% confidence interval. And you see our dashboard gives us the same z-score as the question already. And now it is the lower limit is 27.7%. And here it's slightly different because that question used the rounding variable. So I used the rounded value. So, but the correct answer is obviously from 0.272 to 0.428. So that's A. A university wants to estimate the proportion of students who use the gym regularly in a sample of 50 students. Okay, so now we put here 50. And a success probability of 20, 0.2. Do the normal approximation condition hold? And we can see, yes, it does. And it says, yes, both NP and 1 minus P equals 40. So this is 10 and 40 are satisfied. Yeah, so it is satisfied, but really at the margin, especially for the first one. So yes, the condition is met, and we can see that here too in our output panel. Okay, so now we can go really fast, so that was also a good investment to create such an interactive dashboard. So if a poll of 400 adults, so N is 400, 52% reported owning a smartphone, so that's 0.52, must be an older survey. Construct the 99% confidence interval, so 99. And you see the z-score that we calculate is the same that comes from that question. And now we see that the lower limit is 0.456 and the other one is 0.584. And you see this is where statistical programming comes into play. So, you know, if you use your imagination now a little bit, and you think, all the data that go into a firm, they probably may think, how much confidence can we have in this decision or that decision, and what's the probability of this and that. And having a good statistical programmer might, provide you with lots of good professional opportunities. Anyhow, a researcher wants to estimate the proportion of defective items in a production line to within plus minus 3% with 95% confidence. Using a conservative estimate P equals 0.5, what is the minimum required sample size? Okay. So we assume that the success probability is 0.5. So now we want to know how big does the sample size have to be so that, okay, let's write it and make it clear. So we have our sample proportion now plus minus. The z-score is already given, so that's 1.96. So let's just use this one, times the standard error. So in this case, the standard error is 0.5 times 1 minus 0.5, so that's 0.25. Over n. And this is the n that we would like to have, because we want this term to be less than or equal to 3%, which is 0.03. So we can write 0.03 has to be less than or equal to 1.96 times the square root of 0.25 over n, and we want to know the n. Okay, so what we can do is we solve for n, and the first thing we do is we divide both sides by 1.96. So now we get 0.03 divided by 1.96 is less than or equal to 0.25 over n. Well, now let's square both sides. So then I can get rid here of the square root, and on the left side I need to square that. Okay, and then I just cross multiply, and then I get n needs to be and then it is less than, if I put it on the other side, 0.25 divided by 0.03 over 1.96 squared. Okay, so let's see what we get here. So we say equals to 0.25 divided by 0.03 divided by 1.96 squared. Okay, so now we get 1067, so that is 1068. And of course I made a mistake, because after I cross multiplied, the sign would have to be like that. Okay, so which of the following statements is true about the standard error of the sampling proportion? It increases as n decreases. No. So let's just take a look at this. So we have it here. So the standard error of the sampling distribution is the square root of p times 1 minus p over n. So if this goes up, then of course the standard error goes down. So it equals c and decreases as n increases. This is correct. And it does not require the t distribution for anything. Okay. So what is the next question? A survey of 150 households finds that 45 have solar panels installed. Okay, so the p-value is 45 divided by 150, and that is of course 0.3. And of course I should have put an equal sign around. Our sample size is 150. Okay, so we can assume normality. We don't have to capitalize this one, it looks weird. So, and what is the standard error of the sample proportion? Well, your standard error is 0.037. Okay. And technically what we did is now 0.3 times 0.7 divided by 150, and of that we took the square root. Okay, so last question. As the sample proportion p approaches 0.5, the standard error of the proportion, okay, so again, the standard error is the success probability p times the failure probability 1 minus p over n. Well, if it were 0.1 and 0.9, we get something like 0.09. So if this approaches 0.5, then the maximum value that we can get under the square root, holding constant n, is when p is 0.5, because 0.5 times 0.5 is 0.25. But if you have already 0.4 and 0.6, it is 0.24. So it becomes less, and if you have 0.3 times 0.7, you are down to 0.21. So the maximum standard error, holding everything else constant, is when you have a probability of 0.5. So that is maximized because of this, so that is B. Okay, so that was a long exercise, but I think it was useful to get an idea. Also, not only to understand how we calculate confidence intervals, but it also gave you an idea of what people do when they talk about statistical programming, and it's very useful. But let's just stop here, and then let's continue with hypothesis text in the next lecture. Hypothesis tests. So let's just stop here.